Welcome to the last session of this lecture series. And today we are going to discuss about molecules of a special symmetry. In the last session we have discussed about the molecules with a low symmetry and molecules with a high or a moderate symmetry. And molecules with a special symmetry falls under the category linear molecules and molecules containing multiple higher order axes. The linear molecules again can be classified into two, that is D infinity H and C infinity V. These are the two point groups possible under the category linear molecules, and the presence of absence of I used to distinguish between these two types of groups, that is D infinity H have I and C infinity V doesn't. Okay. So, the group D infinity H is shown by linear molecules like H2, O2, CO2 etc., which are having equal halves. Okay. So, the groups having the elements E, C infinity, infinity times C2, that bisecting the C infinity axis, and also having sigma H perpendicular to C infinity I, and also having C infinity V do fall under the category D infinity H. Okay. So, we have to check whether these all operations contained in this type of molecules. So, the first example we are taking is H2 and N2, which are the symmetrical molecules and having two equal halves. Okay. So, the C infinity axis is this, okay, and there can be infinity times C2s. Here you can see only one C2, like this C2 there can be infinite times C2s. So, it will be like this only, okay, like this in many directions we can draw C2s which are perpendicular to the C infinity axis. Okay. And also there is a sigma H perpendicular to the C infinity axis, and also I, and of course there is infinite times sigma V's also. Sigma V is what? A plane containing the principal axis. Which is the principal axis? This is the principal axis. So, many planes can be possible, like these C2s, there can be many planes possible which are by including the, which includes the principal axis, right. So, here also the CO2 you can see here, the CO2 containing the infinite times C2s which are depicted here, and C infinity axis will be like this, okay, going through the molecule C infinity axis, and a sigma H perpendicular to the C infinity axis, and I is present, and also infinite times sigma V's, that means many sigma V's are possible, infinite times sigma V's. And here also in this H2C2 or C2H2, which is the molecule acetylene CH triple bond CH. The molecule is also symmetrical one which contain the C infinity axis, infinity times perpendicular C2s, sigma H I, okay, and infinite times of sigma V's also present here. So, these are the types of molecules showing D infinity H point group. And in the case of group C infinity V, these are also linear molecules, but they do not possess equal halves like molecules HCl, HCN etc. So, the molecule contain symmetry elements E, C infinity, infinity times sigma V, but does not contain C2 or I. Okay. There is no C2 or I present in the group C infinity V. So, let us look the difference. These row molecules, that is N2, O2, F2 etc. are symmetrical molecules, they do possess I, but these row molecules, that is HCN, HI, C triple bond O, they are non-symmetrical, okay, they do not possess equal halves, so that they fall under the category C infinity V. Okay. There is no sigma H, the plane do not give equal half, So, it is doesn't have a sigma H, and also I is not present. So, the molecule have only which elements? E, of course, these molecules are having E, then one sigma, sorry, C infinity axis, okay, C infinity axis, and also infinity times sigma V's, okay. It doesn't contain a C2 axis, that is an axis through which it can be rotated. It do not give indistinguishable configuration upon a 180-degree rotation, okay. So, there is no C2 or no I is also not present. So, these are the type of molecules showing C infinity V, okay. Now, the second type of molecules are molecules containing multiple higher order axes, okay. Actually, the molecules like regular polyhedra are showing these point groups, okay, and there are in total 7 point groups are available under this category. They are 3 tetrahedral like T, TD and TH, and 2 octahedral, that is OH, O, and 2 icosahedral I and IH. So, these are depicted here. This is the tetrahedral molecule, okay, fall under the category TD. Examples are CH4 and CCl4, and here you can see SF6, which is the octahedral molecule, falls under the category OH, and here there is icosahedral one, which is whose example is Buckminster fullerene, okay, or we say buckyball, okay, C60. It is a ball like structure. So, these are polyhedras which are which falls under this category, okay. So, this type of molecules contain many elements of symmetry, okay. So, for example, here we can look tetrahedral molecule or a tetrahedral point group TD. The molecule contain 24 elements of symmetry, that is E, 8C3, 3C2, 6S4 and 6 sigma D, altogether 24 elements of symmetry. And here in the case of OH, it is 48 elements of symmetry, or 48 operations are different operations are available for a OH group. And here in C60, that means fullerene, there is 120 operations are possible. So, the available symmetry elements for a CH4 or the TD point group are like this: 4 C3 axis, 3 C2 axis and 3 S4 axis, and also 6 sigma Ds. Then how come it be 24 elements of symmetry? These operations can be again splitted up. There are these 8 C3 operations are available. Actually, here you can see 4 C3 operations only, but these C3 operations can be repeated, okay. They are different operations. One C3 can generate a C3 square also, okay. So, likewise 4 C3s generate 4 C3 square also, and there can be a C3 cube also, but it again comes as a identity. So, we are not mentioning that. So, this C3 is again can be written as a 4 C3 plus 4 C3 square. So, altogether there should be 8 C3s, and as in the case of this 3 S4 also, the S4 can be splitted into S4 and S4 thrice, okay. Then two more operations are here also possible. One S4, S4 twice, S4 twice again equal to C2. So, we are not mentioning that. Then S4 thrice, it is a distinct operation, we have to mention that. Then S4 4 times, which again equal to E. So, these two operations we are not mentioning, but these two have to be mentioned. So, this 3 S4 is again can be written as a 6 S4 distinct operations. So, altogether 1 plus 8 plus 3 plus 6 is equal to how much? 24 symmetry operations. Okay. So, the 4 C3s are here represented through each hydrogen atoms, and 3 C2s are possible. Okay. The C2s are also S4, okay, 3 C2s and also 3 S4 equally, and here 6 sigma Ds are represented like this. And now we are able to find the point group of molecules. Okay. So, for that we have a flow chart so that we can easily find out the symmetry of molecules. So, first we have to check whether the molecule is falls under the category special group. If yes, we have to check whether it is linear or other type. If it is linear, we have to check whether it have I or not. If I is present, it is said to be what? D infinity H point group. If it is not having I, then of course it will be C infinity V point group. And if the molecule have a multiple higher order axis, okay, then it falls under the category T, D, OH, O, etc. Okay. So, this we can find out very easily. If it does not falls under the group special group, then we have to check whether Cn is present or not. If there is no Cn, we have to check whether there is a sigma I or a, if there is no sigma or I or not. Okay. So, if one sigma is present, that means it is CS point group. If it is having only I, then it is fall under category Ci, and if there is no sigma or I and it is having only identity as its element, then it falls under the category C1. And if Cn is present, we have to check whether the Cn is a mere consequence of S2n. Then if the answer is yes, and if there is no other symmetry elements present, then the group falls under the category S2n. And if the Cn is present and if there is n perpendicular C2s to that Cn, then we have to if we got the answer yes, there is n perpendicular C2s to the Cn, then we have to check whether it have, then of course that category will be gone to D type group. Okay. Cn and n perpendicular C2s, then it will be fall under the category D, of course. Then we have to check whether it is a DNH or a DN D or a DN, like that. So, if it is having sigma H, then it is fall under the category DNH, and if it is having sigma H, then it is sigma D, then it is DND point group, and if it is having no other sigma, no sigmas present, only this Cn and n perpendicular C2s only, there is no sigmas present, then it will be what? Dn point group. And if there is Cn only, there is no n perpendicular C2s to the Cn, then it exists as Cn only, okay, not goes to the D type. So, it is C only, then we have to check whether it is CnH or a CnV or a Cn, like that. So, if it is having Cn only and there is no other perpendicular C2s, we have to check whether there is a sigma H present or not. If a sigma H is present, the group falls under the category CnH, and if it is having sigma V, no sigma H, then it is CnV, and if it is having no planes of symmetry at all, only Cn is present, then it is falling under the category what? Cn. So, like this we can find the symmetry of a point groups, molecules. Okay. So, let us check with these molecules, which are the point group of these molecules. So, the first one is H2S. Okay. here you can see it is not a special molecule, okay. It is not falling under the special group. So, we have to check for its CN. The CN axis here is a C2, okay. C2 axis is there, and if there is no perpendicular C2s, it is existing as a C itself, CN itself, right. So, here there is no perpendicular C2, so it is having C2 only. Now, we have to check whether there is a sigma H or present or a sigma V present or not, like that. So, here you can see there is no sigma H present because it is a bent molecule, there is no sigma H present, and there is 2 sigma V's present. Which are they? One is like this and one is like this, okay. So, the molecule falls under the category C2V, okay. Once E identity operation is there, C2 is there, one sigma V is like this and one sigma V is like this. Both the sigma V's contain the principal axis, right. So, it is C2V, okay, point group. Now, the second one is PCl3. PCl3 contain C3 as a axis, the axis passing through the phosphorus atom. There is no other C2 axis perpendicular to the axis, C3 axis, right. And also there is no sigma H present, but there is 3 sigma V's, one is like this, one is like this and one is like this. So, the group having C3 axis and a sigma V, so it is what? C3V point group. It is a molecule like ammonia. And coming to this molecule, the molecule have a C3 axis, an axis going like this, and 3 perpendicular C2s are also possible, okay. So, the C again transforms to D type. So, it is D3, okay. Now, we have to check whether it is D3H or D3D or D3 itself. So, here you can clearly see a sigma H, which is the molecular plane. So, it is D3H. The fourth one is a PF5 molecule, and here you can see it is not a special group. So, we have to check for a C3 axis, CN axis. So, the axis is a C3, it goes like a FPF, okay, like this, and there is any perpendicular C2s present. Here you can see 3 C2s perpendicular to the axis, okay. One is like this, one is like this and one is like this, perpendicular C2s to the C3 axis. So, it is transforms to C3 transforms to D3. Now, we have to check whether it is D3H or a D3D. So, here there is a sigma H present, okay. That sigma H is present, which bisects the molecular plane, axis, principal axis, okay. So, the point group is a D3H, there is a sigma H. Now, the next molecule is a XeF4. XeF4 is having a C4 axis, right, and also 4 C2s perpendicular, one is like this, 2 are like this and 2 are going in between the atoms. So, 4 C2s are present. So, the C4 transforms to D4, and of course, since it is a planar molecule, it contains a sigma H. So, the molecule falls under the category D4H, right. And the sixth molecule is a HCCl3, okay. So, the trichloromethane. So, this trichloromethane have a C3 axis present, okay. It is not under the special group category. So, we have to look for a CN axis. It contains the C3 axis and there is no perpendicular C2s, okay, and no sigma H, but only it contains sigma V's, 3 sigma V's. It is a molecule like ammonia. Okay, so only 3 sigma V's are present, so it falls under the category C3V. Now, this molecule is having what? C4 axis. Okay, there is no other C2s perpendicular to the C4 axis, no sigma H, but 4 sigma V's is present for this molecule. So, it falls under the category C4V, right. And the pyridine molecule, in the pyridine molecule it have a C2 axis which is passing like this, okay, and there is no perpendicular C2s to the above axis, no sigma H, but it contain 2 sigma V's. One is like this and other is the molecular plane, right. So, it is coming under the category C2V. And this molecule ethene have a it falls it doesn't fall under the category special group, okay. So, we have to look for a CN axis. So, it contains C2 axis. The C2 axis is present and also 2 perpendicular C2s to that C2, okay. Altogether there are 3 C2s, one can be considered as a principal axis. To that principal axis there is 2 other C2s perpendicular, right. So, the molecule the group of the the notation changes to C2 changes to D2, okay, since there is 2 perpendicular C2s to the principal axis. You have to remember the principal axis is also C2, okay. So, altogether 3 C2s are there, one C2 is the principal axis and 2 C2s are perpendicular to it, okay, like this and like this. So, the molecule also contain a sigma H, okay. So, the C2 transforms to D2 and also it contain a sigma H, hence it is known to be D2H point group, right. And the last molecule is this, that is a trans molecule, okay, trans dichloro ethene. So, this molecule have C2 axis perpendicular to the molecular plane, okay. This is the molecular plane and C2 axis is like this and no other C2s. This molecule contain no other C2s, so it exists as a C2 itself. Now, we have to check whether it has a sigma H or a sigma V. The molecule have a sigma H present, okay. So, it falls under the category C2H, okay. Of course, there arises sigma V also automatically. So, the molecule since the molecule having sigma H, we are mentioning that as a C2H, okay. Now, this molecule BF3 have a C3 axis like this and 3 perpendicular C2s to that. That is, the 3 perpendicular C2s are in the plane and one C3 is going like this. So, these are perpendicular to each other, right, and one horizontal plane is there, that is sigma H. So, automatically there arises sigma V also. So, the molecule falls under the category D3H because it have C3, 3 perpendicular C2s and a sigma H, right. And the ammonia molecule, we know it is coming under the category C3V, right. And here planar symmetrical hexagon, the molecule have a C6 axis, right, and a 6 perpendicular C2s also and also a sigma H, right. So, the molecule comes under the category D6H. Now, we have to construct 3 group multiplication tables. And what is a group multiplication table? Let us look. For any finite group of order H, the possible binary multiplication operations of the group elements can be represented in the form of a table known as group multiplication table. Okay, the binary multiplication, all the possible binary multiplications of a elements of the group can be represented in the form of a table. Okay, and that is known as group multiplication table. So we have to construct group multiplication table for a C2V. Okay, so the C2V molecule, example for a C2V molecule is a water, right? C2Z axis is here, this is the molecular plane, this plane bisects the molecule, sigma V xz bisects the molecule, and sigma V dash yz is the molecular plane itself. So while we constructing this group multiplication table, we have to write the 4 elements, the possible elements in the row and column manner. Okay, the first row can be written like this, our 4 elements E, C2Z, sigma V xz and sigma V dash yz. In the column manner also we have to fill E, C2Z, sigma V xz and sigma V dash yz. Now we have to multiply them, that is the binary multiplication. E into E is equal to E, and E into C2Z is equal to C2Z, E into sigma V xz is equal to sigma V xz only, and E into sigma V dash yz is equal to sigma V dash yz. There is no change. That means this row can be repeated here also. Okay, and this column we have to multiply with this. Okay, E into E is equal to E, E into C2Z equal to C2Z, E into sigma V xz equal to sigma V xz, and E into sigma V dash yz equal to sigma V dash yz only, because multiplying with the E makes no difference. So we have to repeat this portion again in this column, right? Now we have to diagonally multiply this, that is C2Z into C2Z, okay, that is equal to E, and sigma V xz into sigma V xz, it is again equal to E, and sigma V dash yz into sigma V dash yz is equal to E. Now we have to fill the other portions also. Now the C2Z into sigma V xz, the answer will be what? Sigma V dash yz according to the closure rule. Okay, the two operations multiplied, that will be the operation, the resulting operation will be the element of the group itself. Okay, other element. So these two operations when multiplied, we will get sigma V dash yz. So sigma V dash yz will be the answer. And here C2Z into sigma V dash yz. So sigma V dash xz will be the answer according to the closure rule, right? So sigma V xz. And here sigma V xz into C2Z equal to what? Sigma V dash yz, the other operation, clear? And here sigma V xz into sigma V dash yz equal to the other operation, that is C2Z. And here sigma V dash yz into C2Z equal to what? Sigma V xz, right? And here sigma V dash yz into sigma V xz equal to C2Z, right? So this way we can easily fill the C2V multiplication table, okay, group multiplication table. So the C2V point group is shown by the molecules like H2O, H2S, thiophene, furan, etc. Okay. And C3V point group also can be represented like a group multiplication table. The possible binary multiplications are represented by this table. Okay. So the first row you have to write the 6 elements. Okay, E, C3, C3 square, sigma 1, sigma 2, sigma 3. We can represent in other way also, like that, sigma, sigma prime and sigma double prime. So for easiness we can select like this also, sigma 1, sigma 2, sigma 3. These are the 3 planes. So in this column also we have to write E, C3, C3 square, sigma 1, sigma 2, sigma 3, the 3 planes. Now this row is exactly the same and this column is exactly the same, okay, and we have to multiply this to fill the table. C3 into C3 equal to C3 square, Okay, C3 square into C3 will be what? C3 cube, which will be otherwise E. Okay, now C3 square into E is C3 square itself. C3 into C3 square is equal to C3 cube, which will be E. Then C3 square into C3 square, that will be C3 4 times. C3 4 times means from that C3 3 times can be neglected because it is E. So remaining one C3 we can write like this. But filling the other portion is a little tedious process because the operation doesn't yield there is not 4 operation, there are 6 operations. So we cannot blindly pick the one. So we have to perform these operations and then only we have to write it. So if you have don't have enough time to calculate or perform the actions, you can by heart this. Okay, so the E sigma 1 into C3 will be equal to what? Sigma 3. Likewise, sigma 2 into C3 is equal to sigma 1. Like that the operation comes. Okay, so this is the group multiplication table of a C3V point group. Coming to the last group multiplication table, the C2H, we have 4 operations, that is E, C2Z, sigma H, XY and I, that is written in row form and column form, and we have to fill the whole operations in like this. Okay, the binary multiplications available, which are all the binary multiplications which are possible for this C2H point group are written like this. Okay. To summarize, in this lecture series you have been introduced into a new topic, that is molecular symmetry and group theory, right. So it was said that after this lecture series you will be able to identify the point group or the symmetry of molecules, right. So what if we know the symmetry of molecules? Once we know the symmetry of molecules, by applying the group theory principles, we know something about the physical and chemical properties of the molecule. How it come possible? Okay, so the symmetry of the molecule otherwise indicates the symmetry of a Hamiltonian operator. You know about a Hamiltonian operator, which is the total energy operator. Okay, so once we know the symmetry of the total energy operator, that is the Hamiltonian operator, which otherwise indicates the symmetry of its wave function. Okay, so the symmetry of a wave function, if known, then we say that we know everything about the molecule. So the group theory have many applications, like in molecular orbital theory and also in molecular crystal symmetry and transition metal complexes, and various applications it have in spectroscopy. Okay, so this all you will learn in your masters, and these things have to be discussed in this topic, and I would like to wind up the sessions. Thank you. And I would like to thank my professor T.M. Gogulachandran and also the various online resources which helped me in preparing these PPTs. Okay, thank you for the day and thank you for being with me. Thank you.